Now let's move to the next talk of the opening session. The next speaker is Dr. Linfeng Zhang, and he will also give a welcome message on behalf of the other local organizer, AI for Science Institute, Beijing. Dr. Zhang is joining us online, so let's wait a second for the connection. So let me briefly introduce Dr. Zhang. Dr. Linfeng Zhang is the director of AI for Science Institute, Beijing, and the founder of DP Technology. He is also the young pioneer for AI for Science, a very hot topic right now, and he will talk about the future of scientific computing. Dr. Zhang?
Hello? Hello?
Ready? Yeah. So
Can you hear me?
Yeah, yes.
Okay. I'm trying to share the slides, and I'm not sure it can be, is it presented properly, the slides? I just shared the screen. Hello, everyone. I'm Linfeng Zhang, and it's a pity that I cannot join you in Peking University. And I would like to welcome you and thank you for coming on behalf of my colleagues at DP Technology, AI for Science Institute, as well as members of DeepModeling. So actually, DeepModeling is an open source community, and we really learned a lot from OpenFOAM. So my today's topic is on DeepModeling and the way we organize the effort and the way we want to bridge with the open foam community. And so the topic is define the future of scientific computing together. That's the slogan of DeepModeling. So let me start by this question, AI-assisted modeling, why now? So actually I went to Princeton in the year 2016, and I was advised by Professor Wei in the applied math department. And at that time, machine learning just got a lot of attentions because of a lot of breakthroughs in the fields of chess playing, like AlphaGo, and also natural language processing and image recognition. At that time, as a student and majoring in physics and also scientific computing, I was asked and also guided by Professor Wei why we should pay attention to AI, pay attention to machine learning, but we have to look at it in a different way. So what AI gave us? AI gave us models like deep neural networks and what it can do. And in one sentence, this is the one sentence that Professor Wei always ask us. AI gave us tools for representing high-dimensional functions. Image data are high-dimensional data, and also like language data. And also in scientific computing, we do have a lot of problems that can be termed as curse of dimensionality, which means that as the dimension of the problem goes higher and higher, we cannot solve it, even if we know the model behind it and also the governing physical law behind it. And that's the starting point. So if we could have the chance to apply AI to these kind of problems, there could be a systematic breakthrough. And that's the starting point. So then I went to this field of multi-scale molecular and materials modeling. So with this perspective in mind, AI gives us tools for representing high-dimensional functions. We can really just revisit every model we use for the applications in various different directions. So this is a figure with two scales, length scale and time scale, and going from the very basic scale of electrons and ions, we use the Schrodinger equation to describe the system, and we try to solve the Schrodinger equation. However, that's too complicated. And then at the different scales, people have already built up a systematic hierarchical description and scientific models for these kind of events. So going higher, it's density functional theory, and then we throw the degree of freedom of electrons, and then we have atomic scale, and we use molecular dynamics and classical MD to study these kind of events. And then going higher, we have coarse-grained MD and other massive scale models and until continuum models. So basically, we have all these models in this picture. And meanwhile, what we could think of is that given this ability of AI for us to just address high-dimensional functions, what can be changed? Then we will find a lot of high-dimensional functions actually we have been using at all these scales. So here's one example, the potential energy, which is the bridge between quantum mechanics and molecular dynamics. In this case, actually, we focus on this classical MD scale. However, what is in classical MD? Actually, we use that to study various different systems at atomic scale. For example, chemical reactions and also drug discovery and material discovery. At microscopic scale, they always are related to the movements of atoms, and the movement of our atoms are governed by this kind of very simple Newton's law. However, what is not that simple is the potential energy, which is the physical quantity that describe the interaction between atoms. So then there have been a very long time, for a very long time there have been dilemma. So either to use quantum mechanics to solve the electronic structure equations, which give us the energy and forces that drive the atomics to move, or we just come up with empirical formula to describe the different systems that we study, and then we drive the system using this kind of empirical formula. And then definitely because we need to solve the electronic degree of freedom, the first way, the quantum mechanics model could be accurate but expensive. And also the second way is fast but very much limited by the model system that we study. For practical cases, the accuracy has been always the issue. So in this kind of problem, the opportunity given by AI is that we can use AI to model this potential energy surface, no matter for alloys or batteries or semiconductor materials, and also chemical reaction or life science related problems. So that's a unique opportunity, and these are like just taking atomic positions as input and output these energies. Definitely we need to integrate physical constraints, but the unique opportunity is that we can use one single model end-to-end, just like a convolutional neural network, to represent this, so that quantum mechanics can no longer not be the production engine for simulation, but data generator. And after generating a small amount of quantum mechanics data, we could have the opportunity to train an AI model to perform simulation for us. And that gave us a very unique opportunity for various different systems, be it organic molecules or catalysis or high entropy alloys and all these kind of different systems. And that changed the way we do microscopic simulation. And a milestone that we achieved was that in 2020, when bridging AI and physics model, and also optimize that and push to limit on the largest high-performance computer, at that time it was Summit, we could just boost the simulation of atomic system with ab initio accuracy and push the limit to 1 million atoms with machine learning. That was awarded the Gordon Bell Prize of that year. And also that was the first time that we integrate in a very vivid way the three components: AI, physics model, and high performance computing. And then why open source community? And then we always came across this kind of problem: is academic publication system the way to go? Actually, after we proposed all these methodologies and algorithms, we were always rejected by several different kind of journals. So the review process was always like 1 or 2 or even 3 years. So then we have to ask ourselves, given this kind of improvement, achievements, what we wanted to do. And that was actually the beginning of the open source community DeepModeling. So we want to make these kind of new models, new algorithms as new tools for people doing scientific computing. So then we open sourced our first software, DeepModeling Kit, and then build up this deep modeling open source community. And so we have our manifesto. Let me just briefly introduce it to you. So actually what we realized was that the integration of machine learning and physical modeling is changing the paradigm of scientific research. Those who hope to extend the frontier of science and solve challenging practical problems through computational modeling are coming together in new ways never seen before. And this calls for a new infrastructure, new platforms for collaboration, and new coding frameworks, and new data processing schemes, and new ways of using the computing power. And it also calls for a new culture. So this kind of motivation make us like started the deep modeling community. And then actually in the manifesto, we also explained what is deep modeling, why choose open source, and the history of the deep modeling community. And in particular, this was released in 2020, and the short-term plan and long-term vision was that in short term, we focus on microscopic modeling, but in the long run, it is committed to combine physical models at all scales with machine learning methods, using the most cutting-edge computing platforms to solve the most challenging scientific and technological problems faced by human society. So with this vision and this plan in mind, actually, right now we are very happy to see that deep modeling is extending its scope to the scale of reactive flows. And this is a figure, this is the original one, and actually these new places was filled by Professor Chen Zhi, the organizer of today's event. At these scales, we have aerodynamics and turbulence and engine level combustion, and all this modeling or opportunity for machine learning, for example, the compositional dimensionality reduction and turbulence cascade and chemistry stiffening removal. And these are the opportunities that we have seen now in light of the development of machine learning. So then actually we have DeepFlame, this open source project joining deep modeling in the year, I think, 2021, and now we can see it's developed very well right now. And also there has been many recent activities. These are a few votes that we decided the logos were new projects in the deep modeling community. And right now we already have like more than close to 60 repos at different places, the modeling engines and dynamical engines, and also workflows that help us to build up applications or solutions to different kind of directions. So engine level, we have microscopic ones starting from electronic degrees of freedom and molecular dynamics, and also phase fields and DeepFlame or FEM, finite element method solvers integrated with JAX. And these are projects that currently are like very active. And this is the whole landscape of the current status of deep modeling. And then I would like to say, then the question keeps going, AI assisted modeling, why now? So as we can see that in the year of 2020, we all experienced the breakthrough of AI, and we have this product, ChatGPT, released in the world. So the general theme is that AI gives us tools for assimilating truly large-scale data into pre-trained large models, and we have the opportunity to develop large science models at this time. So also that requires a bit more organization than the co-development of software, and we do need joint effort to spend not only on software, but on the large model, on data, and also on the workflows to evaluate and leverage the power of the model. And one example is that after these years of development at atomic scale, right now we are trying to develop universal large atomic model, not large language model, large atomic model for molecular simulation, which takes all these kind of different chemical species or different elements as input, as structures as input, and output properties, physical properties, or directly experimental properties were generated structures. And this is currently based on this, we are having plans like Open Lab on the open source community to build up these large models together with the members of the whole community. And that's the current effort. And also build on this, this is the institute, AI for Science Institute, which currently are holding the are trying to organize the whole effort of the open source community. It was founded by Professor Weinan Yi in September 2021 in Beijing, and the mission, in one sentence, is to empower science and enabling industry. And the way we organized the effort was actually very much based on the open source culture and open science guideline. So right now, because of the development of all these open source solutions that integrates AI and scientific computing, we're trying to extend the scope. And I do think that the collaboration and the current the open forum event will be very important for us to not only to boost this field, but also to have more experiences on how to organize that kind of effort. And finally, what I want to, I do have some deep feeling was that one really need to just keep hands on the all these progresses, and a good way is to not only to just use tools, but to have a feeling on it by these different ways, notebooks and competitions, courses and apps. And in our tutorial, I think we will have, in the tutorial Deep Flame, I think there will be notebooks about it, and one can do it interactively, and there are also competitions. And these are ways on top of open source community that we can just make the solutions better and to really face challenging problems, not only like academic publications. And these are things that we think important right now, and we are spending a lot of efforts on. Okay, so with this, I would like to just briefly introduce deep modeling, and I hope to have very close connection to the open forum community. And thank you again, and let me just stop here.
Thank you, Dr. Zhang. Thank you for your inspiring talk.
Thank you.